Here in question number 9, a point source of light is used in photoelectric effect. If the point source is moved further away from the emitting metal, then we need to figure it out that how exactly the stopping potential will be depending and the saturation current will be depending upon the point source being taken away from the metal surface. Clearly, stopping potential will be depending upon the maximum kinetic energy of the photoelectron ejected, and that will be depending upon the maximum energy of the incident photon. So I would say there will not be any change in the stopping potential of the metal, and definitely as it is taken further away from the metal surface, the total number of the photons that may strike and that may eject the photoelectrons, that may have some reversive effect. So I would say here saturation photocurrent will decrease. Well, definitely that is the correct answer. Option A, stopping potential will decrease. There will not be any effect on this part. Stopping potential will remain same. That's the correct answer. And saturation photocurrent will remain same. That's the wrong one. So for question number 9, option B and C are the correct answers. Now we shall proceed to question number 10. In question number 10, for light wave, which of the following statements are correct? Here the statements are light wave can exhibit the formation of standing waves, beat can be observed with light waves, light wave can be polarized, light waves frequency change while crossing through different medium. What we know exactly, that is light wave will show all characteristic features of a transverse wave. Simply that is the factual answers here. So that means light wave will exhibit the formation of the standing waves, that similarly like the other waves can show. Beats can be observed with the light wave, and light waves can be polarized. So option A, B, C are the correct answers for question number 10. So let's proceed to question number 11 now. Here in question number 11, nucleus A decays to B with decay constant lambda 1 and B further decays to C with decay constant lambda 2. Initially at T is equal to 0, number of nuclei of A and B were 3n0 and n0 respectively. At T is equal to T0, number of nuclei of B stops changing. If at this instant number of nuclei of B are 2n0, then we need to find out how exactly the T0 will be depending upon the lambda 1 and lambda 2, and further what is the number of active nuclei at T is equal to T0. Well, we shall proceed with the standard law of the decay that's been said to be Na will be written down as 3n0 E minus lambda 1 into T, or here the rate of decay of A can be written down as minus of lambda 1 3n0 E minus lambda 1 into T. This is for A. Now for B, I would say the rate with which its number will be changing, it can be written down as dNB divided by dt. How much? This is the way the B has been formed. So it is lambda 1 3n0 E minus lambda 1 into T minus rate of decay of B, that will be lambda 2 into NB at any time. Since it's been given that at T is equal to T0, this was how much? It was 0. So equating this equation with 0 at T is equal to T0, I will have here as lambda 1 into 3n0 E minus lambda 1 T must be equal to lambda 2 into NB, and it's been given that at T is equal to T0, this NB was how much? It was 2n0. Just have this answer here, and from here I'll be getting the value of T0 will be equal to 1 by lambda 1 into ln 3 lambda 1 divided by 2 lambda 2. Is that clear here? Yes. So now on this part, in fact, I calculated it from here itself. It's been like 3 lambda 1 divided by 2 lambda 2 was taken as e to the power lambda 1 into T0. Fine. Putting this value now, I'll be getting the value of Na from this equation. Just replace this value here. It is Na at that time will be 3n0 here. This is E minus lambda 1 T0. So E minus lambda 1 T0 would be written down as in denominator e to the power lambda 1 t naught, it will be 3 lambda 1 into 2 lambda 2. So we are getting the value of Na at t is equal to t naught as 2 n naught lambda 2 divided by lambda 1. Looking onto the options here, for t naught, we are getting option A as the correct answer, and for Na at t is equal to t naught, we are getting option C as the correct answer. Now we shall proceed to question number 12. Here in question number 12, in standard Young's double slit experiment setup, source contains two different wavelengths of lambda 1 to be 400 nanometer and lambda 2 to be 700 nanometer. Options are central bright fringe will be brightest fringe and the constructive interference corresponding to both of the wavelengths radiations would happen. Certainly, I would say whatever be the arrangement here, for any different kind of wavelength that is actually emitted from these two slits, they must be interfering in the constructive manner at the central point, as their path difference is essentially zero. So definitely option A is the correct statement that says central bright fringe will be the brightest fringe as constructive interference corresponding to both the wavelengths will happen. Now next statement is next bright fringe just beside the central fringe is at a distance of 2800 d divided by small d nanometer from the point O along the screen. For this, we need to find what is the fringe width corresponding to two different wavelengths. So I would say the fringe width corresponding to the first wavelength delta W1 would be equal to lambda capital D divided by small d. It would be written down as lambda to be how much? It is 400 into capital D divided by small d. This is the fringe width. And for the second one, it would be how much? It was 700 capital D divided by small d. Looking onto these two options, clearly for every different points or the integral multiple of this part will give us the brightest fringe of corresponding to the lambda 1, and for this one it is for lambda 2. We clearly see that seventh multiple of this one and fourth multiple of this one will give us a point that is common to both of this maxima. That happens to be how much? It is coming out to be 2800 capital D divided by small d. So clearly this one just beside the central maxima will be the brightest fringe. So option B is the correct answer. Now for the dark fringe, I would say here it would be 2n plus 1 divided by 2 into delta W1. For every integral value of n, we shall be getting the dark fringe corresponding to wavelength lambda 1. Similarly, 2m plus 1 divided by 2 delta W2. For every possible integral value of m, we shall be getting the dark fringe for the wavelength lambda 2. So now, looking onto these two options, actually we are not getting a unique values of n or m that will be the integer value which will be satisfying these two equations simultaneously. So now looking onto the option, immediate complete dark fringe just beside the central fringe is at a distance of 1400 capital D divided by small d nanometer from the point O along the screen. That is the wrong option. In fact, I just said that we will not be getting any complete dark fringe. So option D is the correct answer. That says that there shall not be any complete dark fringe on the screen. So for question number 12, we are getting option A, B and D as the correct answer. Now we shall proceed to question number 13. Here in question number 13, in a Coulomb's tube, the potential difference used to accelerate the electron is increased from 24.8 kilovolt to 49.6 kilovolt. As a result, the difference between the wavelength of K alpha line and minimum wavelength becomes 2 times. Use Hc by E equal to 12.4 kilovolt angstrom. Here we need to find out what was the wavelength of K alpha line and the initial difference of the wavelength of K alpha line and minimum wavelength. Let the wavelength of K alpha line, that happens to be lambda K alpha. Now we need to find out what is the minimum wavelength corresponding to these two potential difference when it would have been applied. I would say lambda 1 minimum to be equal to Hc by delta E, Hc divided by delta E. delta E will be the energy. That means here 24.8 kilo electron volt. That comes out to be 1/2 angstrom. Now, further calculation, in case the potential difference has been increased to 49.6 kilovolt. Here I'll be getting HC by 49.6 kilo electron volt. That's the energy here. It is coming out to be 1/4 angstrom. Next statement that is actually given, the difference of the K alpha line wavelengths and the minimum wavelength, that becomes 2 times. That means here I would say lambda K alpha minus 1/2 into 2, that is coming out to be lambda K alpha minus 1/4. If we solve this equation, we'll be getting this answer as lambda K alpha, that is coming out to be how much? It is 3/4 angstrom. So looking into the option, I would say option A is the correct answer. So for the same argument, option B would be the wrong one. Now, initial difference of the wavelength of K alpha line and minimum wavelength. Initial wavelength was how much? It was 1/2, and K alpha line we found it to be 3/4. So simply it is 3/4 minus 1/2, and it will come out to be how much? It is 1/4 angstrom. So that's the answer here. So option C is also the correct answer. So for question number 13, we are getting option A and option C as the correct answer. Now we shall proceed to question number 14. Here in question number 14, in standard Young's double slit experiment setup, S1 and S2 be the 2 slits and C be the center of the screen as shown in figure. If theta be the angle, S1 C S2, S1 C S2, and lambda is the wavelength of radiation, then we need to find out that how exactly the angular position of first minima, and the fringe width will be depending upon the variable given here. What we know here, that this distance d, it can be taken as this angle theta is very small. So should I write it down as theta is equal to d divided by capital D. D divided by capital D, or I would say d would be equal to capital D into theta, theta being very small. Now, angular position of first minima in a standard Young's double slit experiment, what we know, if this is d, then this will be the part difference, and angular position here is phi. So I would be writing down d sine of phi, that must be equal to how much? For first minima it would be lambda by 2, or should I write it down as sine of phi is equal to lambda by 2. For d, we calculated it capital D into theta. So what we are getting here as phi is equal to sine inverse lambda divided by 2 capital D into theta. This is the angular position of first minima. So looking into the option, option A is the correct answer. Now fringe width. In standard calculation, the fringe width that comes out to be lambda d divided by small d. So here it is lambda capital D, and for small d, what was the answer? It is capital D into theta. So here we are getting the fringe width that is coming out to be, it is lambda by theta. So option D is also the correct answer. So for question number 14, we are getting option A and option D as the correct answer. In question number 15, a free nucleus of mass 20 AMU initially at rest emits a gamma photon. Energy of the photon is 14 mega electron volt. Use 1 AMU is equal to 931 mega electron volt per c square. Well, here we need to find out the recoil energy of the nucleus and the de Broglie wavelength corresponding to recoiling nucleus. So clearly I would say this is the energy of the outgoing photon. So the momentum corresponding to this part, we know that it happens to be hc by lambda would be equal to energy, or h by lambda, that's been written down as p, it is delta E divided by c. So if the outgoing photons, it goes with this much of the momentum, then definitely the recoiling part shall have the same momentum, simply because the linear momentum should remain conserved. So I would say the momentum of the recoiling nucleus, it will be how much? It will be delta E divided by C. That will be the momentum, and if this is the momentum, the corresponding wavelength will be how much? It must be written down as h divided by lambda dash. If we calculate this part, we'll be getting the lambda dash very close to 0.9 into 10 to the minus 14, or you may say it is minus 14, or you may say it is of the order of 10 to the power minus 13. So option D is the correct answer. Now we need to find out what is the energy of the recoil nucleus there. So there I would say recoiling momentum, that means m into v, that is the momentum. It can be written down as delta E, that is 14 mega electron volt divided by C, or should I say v is equal to delta E divided by m into C. This is the velocity, and energy would be kinetic energy 1 by 2 m v square, or 1 by 2 m v square is delta E whole square C square into m square, or it is 1 by 2 delta E whole square divided by mc square. Just replace the value of delta E to be 14 mega electron volt. M into C square, it's been written down as 20 AMU, 20 into 931 mega electron volt per C square, and we'll be getting this answer to be very close to 1 divided by 190 mega electron volt. So I would say the option B is the correct answer. So for question number 15, we are getting option B and option D as the correct answer. Now we shall proceed to question number 16. Here in question number 16, the minimum value of D, so that there is a dark fringe at O, that is the D minimum, it's been said. For the value of D minimum, the distance at which the next bright fringe is formed is x. Here we need to find out what is the value of D minimum and what would be this distance so that next immediate bright fringe will be formed. It's we may say just some special arrangement of Young's double slit experiment itself. So looking into the figure itself here, well, this distance from here to here it is D, from here to here it is D. So this distance, if it's taken as x1, this will be also x1. So I would be writing down here the value of x1 to be equal to square root of d square 1 by 2. So from here to here, the total path would be, it is twice of capital X I'm writing down, it is twice of x1. So how much it is? It would be 2d, it is 1 plus d divided by d whole square 1 by 2, or approximately the value of x1 to be equal to 2d 1 plus d square divided by 2d square. This is the path from here to here. So the effective path difference for the wave interfering at this point, it would be delta x. It is 2d plus d square divided by small d minus 2d. So it is coming out to be d square by capital D. This is the path difference. And if it happens to be how much? Lambda by 2. Then we shall be getting the minimum value of this d, so that we shall have the minima at this point. So clearly I am saying here that d minimum, it would be capital D lambda divided by 2 square root. So this is the answer here. So for question number 16, option B is the correct answer. Now further, the wave that will be reaching here is actually interfering in destructive manner, and the path difference was how much? It is lambda by 2. So definitely now, if there would be some distance, so that from here to here and from here to here, if these two paths will be same, then we will be getting the next immediate maxima. Just looking into the symmetry itself, this distance will be same as the d minimum. So I would say the distance x, so that we'll be getting the next immediate maxima, that will be of the 0th order maxima. It will be how much? X is equal to d minimum itself. So for question number 16, we are getting option B and option D as the correct answer. Now we shall proceed to question number 17.